Welcome to our podcast on enthalpy. Now, we've spent some time learning about energy and the way it transfers, and we've done a lab with specific heat of objects, and we've seen how to calculate the energy involved, or in other words, the heat. And so what we're going to do right now is kind of take this a step further and look at energy in kind of an advanced way. And so enthalpy is simply the energy content of a substance. All right. So imagine we've got a substance, and if you guys could think about our last few labs where we've been finding the energy transferred in materials, we've got some energy in here. Now, what is that internal energy? Well, think about it. Molecules are moving, so there's definitely kinetic energy. Atoms are vibrating and rotating, and all that kind of energy. But we can't really measure it. So as you guys know, we can definitely measure the energy change when we take something that's hot and move it to something that's cold and watch what happens to that temperature, right? And so then we can calculate with a specific heat constant how much heat is being changed. Now, heat and enthalpy are essentially the same thing, and for our purposes this year, they are going to be the same thing. Now, before anybody who has some advanced knowledge of this goes nuts, let me just explain. So enthalpy, H, is really equal to the internal energy, and that's all this stuff I'm talking about, plus the work done by the change in pressure and volume. Okay. Now, this stuff right here, guys, is not something we have to worry about at this level of chemistry. It's a little more of a college chem advanced placement kind of thing. But if you think about what happens to the pressure when we do our labs, okay, what happens to the pressure? I'm doing an experiment in a beaker. I got stuff happening. Maybe stuff's boiling, whatever. Who knows, whatever. But what's the pressure involved in there? Well, it's a constant, for our purposes, 1 atmosphere of pressure, right? So the pressure doesn't change. So the enthalpy really equals this heat value, and this heat value is Q. Okay, it's the heat. And actually, you know what? I kind of messed up. I should have made this Q up here before. Okay, so the heat, the enthalpy equals the Q plus the change in the pressure volume, and we've already established that this is constant. So when it's constant, let me get a different color here. When it's constant, the enthalpy of a substance equals the heat involved. And that's a really important thing. And for our purposes in regular chem, honors chem, AP chem even, that's really how we're going to measure it. But it is kind of important to know that there is another factor with enthalpy. But for our purposes right now, we're just really going to worry about the heat energy. And so as before, look up here, it's measured in joules, and the symbol you'll see for enthalpy is H. All right? So this leads to the next thing about enthalpy, and that's the fact it's a state function. And you're going, what? What's a state function? Well, a state function only depends on the initial and final states. Okay. Now, what does that mean? Well, think about when we were solving for specific heat and finding the energy transferred. We only worried about the initial temperature and the final temperature, right? TF and TI. That's all we worried about. So with enthalpy, we really don't care about how it got there. We just are worried about where it ends up. It's kind of like your bank account. You add $100. You subtract $10, you subtract $20, and you could do this over and over and over. Look over a period of a month or a year. You really don't care, right? You just care about how much money you have in your account. You don't care how many times you deposited or withdrew. You just care about the amount that's in there. So a state function is what enthalpy is. And why it's important is because it offers us a big advantage, because we really don't need to measure. Boy, my computer's having a little glitch here. Sorry about this. We really don't need So I don't need to measure it directly. So if we can look up some tables of energies, we can figure out a lot of this stuff. And we're going to definitely do that later when we do something called Hess's Law or do the heat of formation. So it's going to be kind of convenient. But it is a state function that's important. Another property about enthalpy is it is an extensive property. Now what that means is it depends on the amount. It depends on the amount. So, what are some properties that depend on the amount that you've experienced this year? Well, of course, mass, right? Volume. Things like that depend on the amount. And that's different than an intensive property. We ought to probably talk about this one. Intensive. Boy, my writing is horrible. An intensive, of course, is independent on the amount. Okay? Now, what in the world could be independent of the amount? Well, think about this. What about our friend density? It doesn't matter how much you have, right? A substance has the same density. Our buddy specific heat that we spent some time with, those specific heat of water is 4.184 joules per gram degree Celsius. Doesn't matter how much water you have. What's another one? How about boiling point? Doesn't matter how much water you have, it's going to boil at 100 degrees Celsius. So enthalpy, just to kind of summarize, it's the energy content of a substance. It is a state function. We don't care how the path gets there. We just care about the initial and the final. And then it's an extensive property. In other words, the more you have, the more enthalpy you'll have. Moving on to the next thing. Okay, now we're going to talk about change in enthalpy because that's really what we're going to spend a lot of time doing is figuring out the amount of enthalpy change. Just like we found the energy when we transferred, remember we transferred metals from room temperature water. We watched how much the water changed. We're going to do the same thing with enthalpy. And what you'll see, here's a couple reactions that I have. And oftentimes, now this is the first time we've seen it, you'll see this delta H, the enthalpy change, is that much. You've got those two values there. Okay. Now, technically, this is per mole over here. But you will find that books will often omit it, okay? But what this says is if you run this reaction, and this is 1 mole of sugar with 6 moles of oxygen, 6 moles of, oops, this is a typo. How about CO2? Gives you water. That would have a change of 2,816 kilojoules of energy. And since it's 1 mole of sugar, it's per mole, right? Now, what in the world does this sign mean? Look, there's a negative sign there. Okay. Well, what we look at energy as is from the standpoint of this system. So if I'm running this reaction in a beaker, okay, from the system is going to lose 2,816 kilojoules. All right. So from the system standpoint, it has lost energy. Now, by the way, if you've lost energy, what does that mean for us? That means it's an exothermic, right? Reaction. Exothermic reaction. So this sign really tells you if the energy goes in or out, and since the energy is leaving, it's exo. It's an exothermic reaction. Boy, Mike, sorry about this, guys. Computer's having some problems today. Now, let's look at another reaction. Look at this one. This, by the way, is the frozen board reaction that I did for you guys, okay? We added a couple solids. Some of you got to smell the ammonia. We made some water, and there was some barium chloride in an aqueous state. Look at this, 164 kilojoules per mole. Now, do you see the sign here? Well, there's no sign, but since there's no sign, it's a positive sign, right? So that means from the standpoint of our beaker, energy went in. It gained energy, right? So what kind of reaction is that? That is an endothermic reaction. Okay? So this is really important. This sign is really important. That's what this bullet means right here. Sign tells us where it goes. And here's another thing. Don't forget it's an extensive property. So if I have more than 1 mole of sugar, imagine I had 8 moles of sugar, I would get more energy. So depending on how many moles of stuff you have, this value is going to go up or down. If I had 0.1 moles of this, I would get less energy. It would be a tenth of it. Okay? And then here's another thing that's kind of interesting. If these reactions were run in reverse, for example, if I could take ammonia, water, and barium chloride, and I could run the reaction that way, it would actually give off 164 kilojoules of energy. Kind of cool. And then the very last thing, when we've balanced equations and we've done all our stoichiometry, we've never really focused on the states of matter. Okay? They've always been there, but we've never really focused on it. Well, now we kind of got to focus on it because with all this energy stuff, and it's really called thermodynamics, the state of matter is going to start to play a role. It's going to play a role when we get to this thing called entropy, but it's going to start playing a role. So we want to remember that the states of matter, they really do make a difference when we're talking about enthalpy change. All right, on to the last one. I want to give you this one term because you're going to see this once in a while. I don't want it to freak you out, but sometimes you'll see, find the molar enthalpy change of this substance. All right. Now you guys are very good at finding the specific heat and finding the energy and the mass and the temperature change. So this is going to be a no-brainer for you. But there is a new term. We've got this big C, and that stands for the molar heat capacity. Now, when we were doing Q equals C times M times delta T, you guys remember all that, right? This C was the specific heat capacity, right? And it was in grams. Actually, the unit was joules per gram degrees Celsius, right? Well, can you imagine what this unit is? Absolutely. It's in moles. So you can see right here, joules per Kelvin mole, all right? Or mole Kelvin. So that's the only difference. For you guys, you veterans of specific heat problems, it's not going to be a problem. But for the heck of it, let's go ahead and calculate one anyways. How much does the molar enthalpy change when ice warms from a negative 5.4 to a negative 2? All right, so here we go. Delta H, okay, how much change do we have? And so you can see from up here, I've got to plug in that number, 37.4 joules per Kelvin mole, right, or mole Kelvin, times the temperature change. Well, my initial temperature is a negative 5.4 minus my final temperature, which is a negative 0.2, right? And that change is going to be a negative, pardon me, that change is going to be a positive 5.2. Am I doing this right? Let me think about my math. Wait a minute, I think I messed these up. Okay, Richardson brain fart here. Let's put that as my final. Here, let's just go back. It's always T final minus T initial, right? You guys are probably screaming at the screen that I was making my mistake. So let me put this like this, and then I get a positive 5.2. So when I work that out with my awesome math skills, I get 190 joules. Now, guys, this was in degrees Celsius, right? But you guys know that this molar heat capacity, this K I could just replace with a C, correct? Because it's a change here. Now, if you want to add 273 to each of those values and do it, you're still going to get a change of 5.2. I hope you would agree with me. So anyways, the K cancels or the C cancels, and we get joules per mole. And then typically, enthalpy, if you look over here, it's in this kilojoule. So if I'm going to convert it, that gives me 0.19 kilojoules per mole. So there you have it, a little intro on enthalpy. Hopefully it made some sense for you. We'll definitely talk about it in class when we're done, and I will see you next time.